on. Voilà, là maintenant je dois être en on et tu dois devoir pouvoir m'entendre. Et là maintenant ça devrait être le volume comme ça. Test son.
Okay, le volume diminue là maintenant,
Test
le
son.
volume de la musique.
Test son. Test son. Ouais, donc il y a un bon décalage en fait quoi. Test
Ouais,
son.
hop, voilà.
Test son.
Maintenant je dois être en on
Test
et
son.
je t'entends.
Test son.
Ouais.
Tu m'entends bien? Ok.
Ouais.
Bon bah alors parfait, je coupe tout.
C'est ça.
good afternoon. Welcome. Welcome. Okay. So, good afternoon, everybody, and welcome to everybody here with us today and also online, because we are passing the event on streaming. So also hello and welcome to everybody online. I'm Vicky Mosteirin, Managing Director of Greenaway Europe, your host today. So we are delighted to have some of you here with us in our premises. Voilà, so this is the final event of the SmartCHP project, a Horizon 2020 project that has been running since June 2019 until today, November 2023, with 10 partners coming from all European countries, many European countries. And we are delighted to have you here. Indeed, as you know, SmartCHP had a very clear vision and a lot of challenges also to deal with, because indeed cogeneration is the most effective way to generate heat and power. But currently, around 80% of CHP plants use natural gas and fossil fuels as their primary source. Welcome. What is the solution for that? Well, SmartCHP has the solution and has developed a novel bioenergy solution based on fast pyrolysis of local available biomass. This solution is suitable for hospitals, universities, municipal buildings, and a lot of industrial users. SmartCHP proposes 5 different value chains based on different types of biomasses. Different ecosystems obviously mean different biomass types. But as I was mentioning, there has been several challenges to be considered through the life of the project, including public acceptance, cost, obviously legal barriers, sustainability, and all of that we're going to be looking at today in the different working sessions that I'm about to present on the agenda. The good news is that the SmartCHP has achieved some very important milestones, including to be the first time ever to have 1,000 hours of running the SmartCHP engine without any disruption, and we are very happy about that. The system has proved to be sustainable, very sustainable, and ahead of all of the European Union targets. And obviously this is something to be very well considered. 89% emission reduction compared to the fossil alternatives. And this in the 5 value chains that SmartCHP considers. When it comes to public acceptance, which we know is vital, this is also good. We know that countries like Sweden, Croatia, and Romania, they have a greater social acceptance. And the other countries like the Netherlands, where social acceptance has proven to be lower. So this is also something to take into account. And that's why we are more convinced than ever that communicating the plans to install the SmartCHP systems is vital. And policymakers need to be involved. We have also looked at market analysis and financial sustainability. Dowell, one of our members, has done a wonderful job on this. And also SmartCHP approves financial sustainability as the systems are flexible and can be combined with other means of renewable energy production. And the last point that we will also be looking at today is on policy recommendations that the project has produced. We know that these technologies are considered key by the GRSC, and very valuable for future energy systems. And for this, they should be a must in all the national energy transition plans that the member states prepare or are still preparing. Finally, today we will be listening on how the SmartCHP partners advocate, among others, to develop a market introduction program in collaboration with national authorities, including the installation and monitoring of a number of SmartCHP installations, allowing to produce data and to facilitate all permit requirements. With this very brief intro, trying to touch a little bit all the aspects of the project, we have 3 different sessions today. We will be touching technology, market, and policy. And just to remember all participants that you can make questions via the chat on the live stream. First session will be on technology. And if there are no questions or comments, I will invite the wonderful coordinator of SmartCHP, Bert van de Veld from Biomass Technology Group, BTG, who has done a great job and who will be leading this first session. We will have a coffee break around 3:20. No? Thank you. Please.
Thank you for this introduction. Good afternoon, everyone. Also from my side, welcome to this final event of SmartCHP. It's always a pity that a project comes to an end, but still we would like to share some resources we obtained. What I will do is give maybe again a short introduction on SmartCHP. It was partly done already by Vicky, but a little bit about the background and the activities we had in the project. And then focus in the second part, focusing more on some technical research we obtained, and in particular on running the engine on fast pyrolysis bio-oil. And that's, I think, a core activity within this project to do so. So first, a short introduction on SmartCHP. What we would like to develop, and that's in fact the main objective, is to develop a novel, flexible, small-scale cogeneration system. A small scale means, let's say, 100 to 1,000 kilowatt electrical, producing the heat and electricity. And what we also realize is that fuel cost is a major cost component in such system. And that's one of the reasons we would like to use untreated fast pyrolysis oil. So just crude pyrolysis oil as it is normally produced, and use it directly to minimize fuel cost. And this pyrolysis oil is produced from all kind of different biomass resources. It can be agriculture, it can be woody, etc. A big advantage, what we use is so-called compression ignition engine, normally known as a diesel engine. And the big advantage there is that you have relatively high efficiencies, and moreover, you can have very fast startup and very fast load changes. So as mentioned, we foresee commercial application in this range from, let's say, 100 to 1,000 kilowatt. And what we also would like to achieve is a high heat to power ratio, or to be very flexible in the output, having more or less heat compared to the electricity. Well, schematically it's shown here. We start with non-food biomass, and the RED 2, RED 3 compliant biomass. We make fast pyrolysis oil, and this fast pyrolysis oil, FPBO, is fed to the engine. And, well, of course, we need to modify this engine. And then the flue gas from the engine is sent to a boiler, and we can add some additional pyrolysis oil if needed, if we need more heat. That was the idea. If you have a low electricity demand, you have a lot of oxygen left in the flue gas, you can easily add a little bit of pyrolysis oil, making more heat. That would need a smart control to have the optimum operation point. And we have the heat and electricity, and it can go to multiple sectors. What you see is all the different activities we had in the project. A range of, the blue ones, the technical activities. It's developing certain components, like the boiler, like the engine, like a flue gas treatment, also do some modeling, etc. And it should all lead to the development of what we call the prototype. And the prototype is, in fact, it's 48 kilowatt electric diesel engine running on pyrolysis oil. And that should provide the information for a commercial scale system. Besides, let's say, the technical aspects, we have some assessments on biomass availability, market assessment, techno-economic assessment, but also the sustainability, socio-economics, and policy. That will be covered later in this program. I will focus more on on the development of this prototype. These are the partners in the project. We have 10 partners, 6 different countries. Initially it was 48 months. We got an extension of 6 months due to Corona. We started in June 2019, so it will end by the end of this month. So this Thursday we have the formal end of this project. And the total budget was around 4 million euro. And here we have all the partners. That's just as an introduction in SmartCHP. We will hear more about it later on. And I would like to continue only with the fast pyrolysis and the application of fast pyrolysis oil in the engine. First, fast pyrolysis, probably well known to most of you. It's just depolymerization of biomass, a thermal cracking. No or very limited oxygen. We normally run without any oxygen. And we really aim for the liquid product. So we try to maximize the liquid product, what we call the fast pyrolysis bio-oil. That's the product we will use in this project. We have some other products, gas and char. The gas and char will be used within the process to generate the heat or even process steam and in certain cases electricity. The technology itself is maturing. There are commercial scale plants running. Here is an example of Finland, one in the Netherlands. Typically, these installations have a capacity of 25 megawatts, so roughly 5 tons per hour biomass input. And it also would mean that one pyrolysis plant would be able to provide the fuel for many SmartCHP units. Typically, it's sawdust. The commercial plants at the moment is mainly sawdust or clean woody residues. We also look to residues of, for instance, agricultural residues. They are normally cheaper and might be make the overall system cheaper. But commercially, it's mainly wood. Well, then we have fast pyrolysis oil, and well, it's available, it's sustainable, that's good. It's a liquid, but it's not really an oil. The properties are completely different, and that makes it also challenging to use this oil directly in engine. Well, just for comparison, pyrolysis oil and diesel, and the impact on engine operation, we have water. And that's normally not good for a fuel injector. It leads to corrosion, erosion. The density is very high, or it's higher than a diesel, and that's a negative for atomization. Atomization is better at low densities. The heating value, 16, diesel is 42. So it's more difficult to get sufficient energy into the engine. Carbon residue, it's the sensitivity, it limits in fact the heating up of the oil. We cannot just preheat the oil to any temperature. It will produce a lot of carbon. So that's a difficult one. Acid number, it is acidic. It contains a lot of organic acids. It also means that it will corrode normal injectors. Viscosity is a little bit higher than for diesel, bad for atomization, same for surface tension, it's higher, also bad for atomization, so it's difficult to get very fine droplets upon atomization. And the C10 number is a good indicator for if you can ignite the fuel. The higher the C10 number, the easier it is. While for diesel, normally they want to have at least, let's say, 40, 45, and we are certainly below 20. That makes it very difficult to ignite pyrolysis oil in a diesel engine. Well, later on we will see an approach where the pyrolysis oil is modified and then use it in a turbine. What we did here on purpose is not modifying the fuel. We have the fuel as it is, and we modify the engine. So it's the two extreme approaches. So we modified the engine. We have different facilities at BG, what we call a 1-cylinder research engine and a 4-cylinder prototype. Some properties are given here. But to be able to run the engine on pyrolysis oil, we need certain modifications. So what we did, we increased the compression ratio. And increasing the compression ratio means a higher temperature at the end of compression, and you can ignite the fuel. That's also the reason we did some air preheating. If you start with a higher temperature, at the end of compression, temperature will be higher, easier to ignite. We did a little bit of pyrolysis oil preheating to lower the viscosity, but it's limited, because otherwise it will polymerize. And a difficult one is to have this corrosion-resistant fuel injector to be able to run continuously. And of course, in the end, you need to have low emissions, and that's the reason we added a flue gas treatment. It's a kind of an add-on to the system, but to be able in the end to comply with European emission limits. This is the 1-cylinder test engine. In fact, it's a 3-cylinder engine, and 2 of them are made inactive. So in fact, it's originally 3 cylinders, 2 are inactive, only 1 is running, and you have only to install one new fuel injector and one modified fuel pump, etc. It's easier for development. And so this is the engine, the fuel feeding system, and there is an automatic control system that you can easily switch from one fuel to another. Well, we did a lot of experiments. I won't show you all the results of all the experiments. There are some public deliverables explaining more on the results, but of course we looked at different process parameters. Well, just looking at the process oil, it's not treated. The only thing we do, we filtrate it, at least to avoid that there are particles in the oil. And very often we add a little bit of ethanol because that makes life a little bit easier for us. It's the lowest viscosity and it's easier to feed it. If there's a subscript like here, 10, it means 10 weight% of ethanol has been added to the process oil. We looked at different process parameters. We looked at process oil from different resources like pellet crumble, sawdust, miscanthus, olive residue, and also a fraction of process oil, which is called pyrolytic sugar. We also used it in the engine. And we compared it to reference fuels, diesel, but also ethanol, butanol, and also hydrotreated vegetable oil. It's easily available and just for comparison. The long-term testing we did with what we call GFN, but GFN is the oil from Finland, and we can easily get it. And so a lot of long-term testing was done with oil from sawdust. Just some results. What you see here is the different fuels, and all these are process oils, and these are reference oils. Of course, if you look at the mass of fuel you're injecting, it's much higher with process oil because the heating value is much lower. That means that you have to inject 2.5 times the mass of diesel, because otherwise you have less energy entering the engine. So that's quite normal. The same you see for ethanol, butanol, because also the energy content is lower. The yellow one is on an energy basis, and as such it looks quite nice because diesel is set to 1. And in fact, if we compare it on energy basis, we consume a little bit less process oil. Of course, that's very good. But I also have to admit that the engine has been optimized for running on process oil. It means the conditions are not optimal or suboptimal for diesel. But basically, it's roughly the same. And what you see here, this is what you would expect. If you change the heating value from the fuel, you get this kind of line. And in fact, the red line means it's the same energy efficiency. But what we see normally is the energy efficiency on process oil or diesel is roughly the same. This was an important one. It's the 500-hour milestone. Initially in the project, we said what we would like to achieve as a very important milestone is running 500 hours this diesel engine without changing the fuel pump, fuel injector, just running as stable. Don't change anything. So that's what we did here. And then we look at the emissions, NOx, CO, and we also look at the exhaust gas temperature. What we see normally, if there is a really wear on the injector, we see a very rapid increase in the exhaust gas temperature. Of this 500 hours, first this is, you see a little bit increase in CO, maybe also in NOx, but for us the changes are very limited, and this was for 500 hours without any problem. We were continuing this testing also for flue gas treatment, etc. So this injector we used here at least was operated for more than 1,000 hours on fast process oil. I think that's a quite good result, and I think a major result from this project. There were some other pictures, but apparently there was an animation here, so it disappeared. I think so. There was an animation. Well, there were some more pictures of the engine. It's not that important, but this is the 4-cylinder engine. Well, you can see here we have the 4 different injectors. These were made in-house, so we are making our own fuel injector and also fuel pump. It's a kind of a combined system, so the injector contains also a fuel pump component. That's quite specific. Have been completely constructed in-house with injector, with a measurement point, etc. Well, you can easily see it here. You just have to drill some holes in an injector, and I think the holes we are drilling is something like 250 micron. I can't do it, but I have a colleague who did it. And of course, you can do it for 1 cylinder. You have to do it only once. If you go to 4, you need 4 identical ones, and that's still quite challenging to do. But in the end, we managed to do so. So this is part of the 4-cylinder prototype. 4C prototype, and so this is also the emissions directly after the engine, so without any flue gas treatment. And again, we are just comparing diesel and pyrolysis oil. As said, also the 4 cylinders optimized for running on pyrolysis oil, not optimized for running on diesel. So I think also with diesel, the performance could be a little bit better. But what we normally see, and this is the NOx, with diesel, the NOx is always a little bit higher. And I think it's burning a little bit, we can achieve higher temperatures. The rest of conditions are the same. And of course, if you go to regulations, this is very high. And far beyond any regulation, and you will always need flue gas treatment for both. And I think the limits are somewhere very close to the excess. I'll come back to that. Same holds for the CO. Up to a certain point, it goes, I think, up to 80% load. It's acceptable. And then suddenly, if you increase it further, then we see a very quick increase in CO and NOx. And in CO, it means burning becomes quite poor, and CO goes up quite rapidly. So up to 80% is quite okay. If you go to 100%, both for diesel and for pyrolysis oil, so it's apparently part of this system. Soot emissions, we do not really measure soot. It's what we measure is opacity of the flue gas, and it's a little bit indirect. It's not an absolute guarantee that the particle emissions are very low, but it's the only analysis method we have so far. And actually at the moment we are trying to do the particle measurement, but the results are not yet available. What we see again is that for this engine, this is almost to 100%, the opacity remains very low. It would be an indication that soot emissions are quite low with this system, but it's not a guarantee. Here again is the electrical efficiency of this engine. According to the engine supply, it should be 32%. Anyhow, in the project we were hoping for 40%, but if we start with an engine which is designed for 32%, we will not be able to go much higher, or we will not be able to go higher. But what you see here is diesel and pyrolysis oil again as function of the load. And we are around this 31 to 33%, somewhere in that range, if we run at sufficient high capacity. And I think also the conclusion here is that it's, apart from the absolute value, there is hardly any difference if we run on diesel or pyrolysis oil, and I think that's quite nice, quite good. Well, of course, as mentioned, the emissions are quite high without any flue gas treatment, so we need a flue gas treatment. Well, it's the engine, we have the flue gas, all the measurements so far we're in from this point. Then we have now an oxidation catalyst to get rid of the CO, the hydrocarbons, and it's also a particle filter. Then after that, AdBlue is injected, the ammonia solution. We have catalytic denox, and then we should have the clean flue gas. At least it should comply with the with regulation. Here you see some results from the 1-cylinder engine at fixed conditions, and there we also needed this at least 100 hours of operation. This one was running for 150 hours without changing anything. So after the start, the red one again, the CO, and the blue one, the NOx, both were somewhere in this range of 92 to 96% conversion. And then also the emissions are within the limits. We think this system for the 1-cylinder, and we have the smallest one from TEAG. I still think for our research engine it's a little bit over-designed, and that would also result in these very high emissions. But the catalyst remained stable. Of course, we did the same for the prototype, because that was, in the end, that was the target. Here you see a picture of this flue gas treatment. This is the oxidation catalyst and the particle filter. Here is the part with ammonia injection, the same as here. And at the end, the NOx is this part. So it's from two different angles. It's the same system. Of course, when we operate it, it's insulated. This is a picture just before installation. And we did the same testing. And what I plotted here is, for CO, actually, there is not a regulation for CO. So but in the project we defined our own performance indicator that it should be below a certain value. This is the green one. The blue dots are from experiments. And the same we did for NOx. As function of runtime, we were operating this prototype for 100 hours. The red one is EU regulation, and somehow we ended up with a performance indicator in the project. We defined it, and that was extremely low. Apparently its values for boilers or from Germany, which is more strict than any other country. But we plotted here both. So if we operate the system properly, we have the emission limits at least below European emission standards. Only in a few cases we were able also to, what you see here, only a few dots we have below the performance indicator we defined in the project. But it seems that was a little bit too ambitious to have it throughout all conditions. But at least we are able, I think we know now more or less how to operate the flue gas treatment, that we are within the limits. The same holds for CO. One final one. As mentioned at the beginning, we would like to have flexible heat. And maybe we will come back to in one of the other presentations, but our idea was if we have a low electricity demand and a high heat demand, it's easy to add pyrolysis oil to a boiler, generating more heat, and then we have very flexible output, low electricity and high heat demand, or vice versa. If we're running the engine at 100%, there is no oxygen left in the flue gas for additional burning, so it's only for low electricity demand. And this is the original idea. We have the engine, this is the pyrolysis oil input to the engine. If we are running at low electricity demand, let's say the green one, and of course we get heat from the engine, but then we have still flue gas with a lot of oxygen and a high temperature, and that should be easy to add a little bit of pyrolysis oil, generating more heat. That's basically the idea of SmartCHP. So we added this boiler. That's one way. The other way could also be we have the SmartCHP engine. We have a low electricity demand, but we can also then feed additional pyrolysis oil to the engine. We generate more heat on the engine, and we have excess electricity. We generated excess electricity, and we could also do it then by an electrical heater or even a heat pump. And then what we did in the project in the last part is this was the original idea. If we look at the two systems, we think this is probably easier to implement and to get this flexibility. Of course, in course of a heat pump, when you are able to use a heat pump, you can even have a very high heat output. What appeared here, and honestly, we still are not 100% able to run the boiler in this setting. It's very unstable, or it's hard to ignite, and so we had a lot of complexity. And actually, we also running the system with electrical heaters. We also have it in the lab. It's much easier and simpler to operate, and let's say the changes in load or output, it's much more flexible. So I think in the end, for the next system to implement, probably it will be more a system like this than a system like the first one. But that's also an outcome of this project. Oh, anyhow, what at OWI in Germany, they were running the boiler standalone with pyrolysis oil. That works. But this combination, this integration creates a lot of complexity, and so that was not fully successful. Well, to summarize, well, I think we were able to modify the combustion engine and really to run on pyrolysis oil as a fuel. What we also saw is that even if we change the origin of the pyrolysis oil, it does not have a major impact on running the engine, as long as the oil is more or less homogeneous, or you have to treat it. We cannot run it in a two-phase oil. Well, the engine, we ran it at least a one-cylinder engine for more than 1,000 hours, but also the prototype was running for more than 100 hours. We saw very limited fouling, so we were very happy with this pump and injector. Apparently, the solution we have now does work for this system, and that took quite a while. Flue gas treatment it's effective. At least we can stay within European and Dutch limits, but as mentioned, we did not fully achieve the performance indicators we defined ourselves. Another one, if you compare diesel and pyrolysis oil, is very much the same. If you look at electrical efficiency, that's also quite good. In that sense, there is no D rating. It's hard to run at 100% engine capacity. And then the last one, if you look at the electrical efficiency, that's also quite good. In that sense, there is no D rating. It's hard to run at 100% engine capacity. And as the last one, what we also saw is that from a technical point of view, and you want to have a high heat to power ratio, it's easier to add or run or to feed the engine with more pyrolysis oil, generating more electricity and use that for heat generation than injecting the pyrolysis oil and additional in the flue gas. Creates a lot of complexity, difficult to control, and therefore I don't think that's the proper solution in the end. There's a website, there are also movies, there's also moving on the engine, so you can go there. And that brings me to the end. Thank you.
Thank you so much, Bert, and congratulations again for the great work and all the achievements. And I think we have some time for questions after each of the sessions. So if there are any questions, now or never, please don't be shy. No questions, maybe later. Okay, we have a question here. I can go. Thank you, Peter. Please introduce yourself.
Hi, Alan Sherrod from Bioenergy International. What's the next step after this project?
There are two different approaches we are looking at the moment. One is within the project we also made a design of a 250 kilowatt system. That would be a nice demonstration size. And the other thing we are looking at the moment in our lab is that the size of this prototype matches quite well our electricity demand in our process hall in the laboratory. And we were looking whether we could just combine it, so running the engine and just covering the electricity need in our own lab. And apparently they told me that's not very complex, but I haven't seen so far how it will work exactly. But that would be a nice one, because then you can keep on doing the demonstration. At the moment we are just heating the building by a lot of electrical heaters and heat from the engine. But I think the next one, or probably both, a full demonstration will be 250 kilowatts. But I think the demonstration value would also be quite nice if we can combine it with our own building and reducing, let's say, external heat and electricity.
Thomas Schlecke, European Commission. So thank you for the very interesting presentation. I have a question regarding not CHP, but how you think your results are useful. If you think about transport, I'm thinking, for example, maritime. Do you see an application there, particular about what you learned here?
If we go for pyrolysis oil, and maybe it's partly covered by the presentation of Michel, because that's the upgrading of pyrolysis oil. There are some possibilities to use, let's say, pyrolysis oil directly for certain applications, also for transportation, but that's more co-refining. Direct use in maritime, I would say then we would go for upgrading and make something which is compatible with the marine fuel. And the same holds for instance, if you make aviation fuel and marine, you can do it in parallel. But that makes it compatible, and I think it will be very hard to have crude pyrolysis oil using it on board. That's I think a quite hard one. Yeah.
Thank you very much, Bert. Any other question? Also, everybody online, don't forget you can make questions in the chat. I don't think we have any yet. Thank you. So thank you very much, Bert, and we will continue the discussion later. Yes. So I forgot to mention that the building has had a problem with the projector. That's why we need to use that. We only knew Friday night, so unfortunately we couldn't pass the videos because there's some limitations. I don't know if maybe at break we can do something for the video. Anyway, so we continue with our technology session. And now is the time for Enrico Bocci, Associate Professor at Università degli Studi Guglielmo Marconi in Italy, who is going to be presenting us the SO3 and Blaze projects. So thank you, and the floor is yours.
Thank you, Vicky. Yes, okay, so... Okay, so thank you much for inviting me. I hope not to bother you too much, okay, but the matter, as Bert said to us, is complex, so some bothering is mandatory. So, More or less, I will talk about the Blaze and SOFRI project that are similar, okay, so with smart CHP, okay, project with different technology, okay, but the things in biomass are more or less similar. Okay, first of all, the status of the CHP. There is a status that we have also together for the biomass availability, okay, but there is also status on CHP that we also check a little bit together. There is deliverable in the Blaze and also Smart CHP website that I suggest you to read about biomass availability and so on, CHP status. So more or less, this means that the CHP is mainly done by steam turbine, okay, or combined cycle, okay, at a bigger size, no, okay, not at this of a Smart CHP. And there is also small operating hours, okay, so 3,000 operating hours electrical and 2,000 thermal, okay. So also this is no. I want to do a AI efficiency. I want to make a better efficiency use of my energy, no. And after I have to plan to have a system that is operating to 3,000 per year, not 3,000 per year, no. Okay. So this is also things, okay. The cogeneration electrical now it's average 40% electrical and thermal, so there is more thermal needs. Okay, it's mainly used for space heating, process heating. Okay, and we saw the countries now that use mainly CHP. And in smart CHP, you see the country use mainly biomass. Always Germany, Italy, there is UK, Sweden that use biomass. Instead, here the money that use main CHP and biomass. CHP, Poland also, and of course there is also Netherlands in the other. Okay, so this is more or less. Regarding the fuel, is mainly used natural gas. Okay, but biomass is increasing. Okay. So there is a lot. There is a use of biomass for CHP, okay, and below 1 megawatt electric megawatt are mainly used biomass combustor coupled to organic cycle biomass gasifier fixed bed coupled to internal combustion engine. This is regarding, for example, the CHP. The other part is regarding the gasifiers. Gasifier is for 200 years, okay, more or less, okay. And each time, okay, each people invent this particle. We think that with Coordinated Unify and Bliss project, we think that the double bubbling maybe is more compact to alpha bed gasifier. And so we patent these two double bubbling gasifier. So instead to have the circulating, okay, here, no, the two circulating, okay, the Battelle, Columbus, and so on. The, for example, you remember, no, the Bauer and so on, the technician in Vienna, no, circulating and bubbling. We put to bubbling, okay. That for us is more compact, okay, in order to allow the application of the reactor for the small, medium, okay, sites. So there is the idea of this biomass, low-cost, advanced zero emission, no, small to medium scale integrated gasifier, fuel cell, combined heat and power plant, okay. And here instead we make always the waste biomass, okay. We use instead this double bubble gasifier. We produce a syngas to send to the soft, okay, and to produce heat electricity, okay, more or less, okay. So there is here also the problem that maybe for industrial we can increase the annual operating electrical thermal operating hour. That is good, okay. We can arrive to 7,000. Okay, if you have some industry that use continuous electric and heat, okay, but of course here the price you have to say is a little bit low, okay, and of course there is also the problem of the price of the feedstock, okay, that is not 60, 100, but we saw in these days also 300 euro per tons in the past months, okay, when there is the war in Ukraine, okay. So, what is the target of Blaze? To reach 90%. So, with the soft, maybe instead of internal combustion, we can also reach maybe 50% of efficiency, overall efficiency. The soft have also a stack efficiency that is greater. Okay. And so, this is the capex and so on. These are the target of Blaze. Okay. We divide within different work package that you will see. And this is our gasifier with the hot gas conditioning, the attachment to the anode fuel cell. Okay, and of course also as we think about to burn also in order to have a different percentage of heat electricity, okay, because of course the gasifier and the soft is a stable operation better, okay, and so it's better to have an alternative. Also here there is some partners, research center and companies partners, okay, from some European country. And also here we have some category of feedstock. we are mainly interested mainly for gasification, and so we are most important to ash melting point, okay, in the reactor, in order that they don't melt in the reactor, okay. So there is also if you see in the Blaze Derivatives that it's open, you find all this data and regarding all the different melting point temperature for the different ways that we check. Of course, there is the problem of the cost that we check. Okay, also in order to harvesting this biomass, okay, because the SmartCHP you also have a good option. Instead of I have a big plant when I arrive all the biomass, and after I send to the little small CHP the pyrolysis oil. Instead, here we have to take all the biomass to the gasifier. Okay. After there is the results about the primary condition, okay, the condition we find within the reactor, and so it's mainly made by, for example, calcinated dolomite, olivine, and so on, in order to decrease. This is the lab of Enea, okay, and there is results about the decrease in contaminants for this primary condition using instead of natural sand also calcinate dolomite and olivine. This mainly the best thing is 50%, okay, of percentage, additional percentage. Also, we put here catalyst inside the filter candles, ceramic filter candles. This is a lab scale, okay, in order to decrease the content of the tar and to avoid zero particulate. Okay, these are the results. Finally, as we see again, so in this room, we test the sorbents, okay, so the high temperature sorbent, in order to decrease the contaminants, absorption of the contaminants. For example, for H2S, we found that also we can use the low-cost zinc oxide. There is some sublimation of the zinc oxide, but the resin gas is water and is not too much, okay. So we can also increase the use of zinc oxide that is used up to 400 Celsius degrees, up to 500, 550 Celsius degree, more or less. And we dimensioning the secondary reactor for that, hot gas temperature. And the work package 3 is the solid oxide fuel cell. And so there is many tests about the bottom cell, so a few centimeters of cell, in order to understand the process. So what happened to the different contaminants? Think about that we send hydrogen, after we send, with the blank, in order to understand. After we send CO, after we send CO2, after we send CH4, and after we send together, okay, up to arrive to the different syngas evaluation that is composed of hydrogen, CO, CO2, CH4, okay, and also we take two tar representative for the toluene and naphthalene as the target. More important, maybe important, different analysis were made by PFL within the stack. Okay, within the stack we arrive at more than 2,000 to 22,500 hour operation of the stack. Okay, so for example, with the ppm of H2S, we have 3,700 hour operation. Okay. And also with toluene and naphthalene and so on, okay, also with HCl, okay, and we saw some phenomena. That's also different from the bottom to the stack, of course. But in general, okay, we found the right limits for the ppm of H2S and HCl, and so we dimensioning the hot gas temperature sorbent for that. Regarding the model activity, we model in CFD the double bubble gasifier. We model in the CFD the filter with the catalytic filter candle. Okay. The problem is that okay, we need also to push the gas. Okay, it's not an internal combustion engine, so we need to push the gas. And so in order to push the gas, we have to develop a steam driver blower in order to push the gas, okay, without oil, and so the gas beating here and here, okay, so a complicated blower, okay. Of course, we make all the plant over a plant and all the out gas condition system in a container, okay, and we are responsible instead for the overall Aspen simulation. Regarding the modeling, think about that we have more or less 40,000, 40,000 configuration of Blaze, okay? So this was a Pareto analysis of the different type of configuration in order to understand what can be. So think about that. No, you can this is only for 3 main operation of the plant, okay? And we analyzed that, of course, the anode gas to the gasifier combustor was the best one. The other was not good. Okay, but these are, for example, 3 main, but there is a very different combination of heat exchanger and so on, okay, and different flow that can be managed, okay, configured. And so we have a different, more than 40,000, and we make this analysis taking into account the best electric efficiency, thermal efficiency, and heat exchanger network, reduced heat exchanger network area, okay. So after, think about that, after the 40,000 model analysis of different process, possible plant, we choose 1 plant to build. And in this plant, we made more than hundreds of P&I, okay, in order to control all the overall system, okay, mainly the one of Nereco regarding the gasifier, the one over here regarding hot gas conditioning, okay. So we build the plant, okay, it's 100 kilowatt gasifier with 25 kilowatt soft, okay, instead of 50, okay, because Solidera was made in the 25, and we test at 25, and so we operate the gasifier really stable, the gasifier with the temperature with a good hydrogen composition, okay, and also we had a better composition for the hot gas conditioning, and this more or less the things. About there is also the techno-economical, social, environmental assessment. Regarding that, of course, we need first that, for example, the solid oxide decrease the cost, okay, because they have to go up to 4,000 euro per kilowatt, okay, otherwise it's not possible to apply conveniently the plant. Regarding this is mainly regarding the capex. Of course, there is some things, okay, that start also for the model analysis of different configuration. So we don't have to use additional fuel. Okay, we have to use the off gas directly to the combustion in order to not to have additional fuel, and we have to have a very good heat integration. Okay, self-produced steam. Okay. And for example, if we use always here in the plant LPG, instead, of course, for environmental assessments, better to use biofuel, okay, more or less, and to use, for example, renewable electricity instead the grid electricity that you use, okay. This is for general assessment, okay. And so maybe we can reach the target if all these conditions will be respected. For application of that, it's better to apply that in a case of industry when there is already a fixed heat and electricity demand, okay, and already, for example, have a boiler in this case, okay, for having the heat, the process heat, and so substitute the boiler with the gasifier and the solid oxide fuel cell can be a good option. And so we have also a good evaluation, of course, with this kind of cost of a large stack model of the soft. Okay, so 5 years lifetime and 40,000 euro per kilowatt. That are more or less than the double that what we had in the project. Okay, so these are half of the cost that we had in the project, more or less. Okay, this is more or less the things. Okay, regarding the dissemination, we disseminate together now in the European Biomass Conference SmartCHP. We create together Cogeneration 2030. Okay. And okay, this.
I was thinking, thank you. I was thinking maybe we can see if there are any questions on Blaze before going to Sophie.
Yes.
Maybe it's better.
Okay.
So we don't mix the 2 projects.
Yes. If you.
Are there any questions on Blaze?
I was just wondering, you built the integrated system, gasifier and solid oxide, and there was one result, but how many hours did you operate the overall system in total?
The overall system, 0 hours.
Few hours.
Okay, so the overall system, we operated 0 hours. The gasifier was operated for 2 years, okay, so more or less 8,000 hours, okay, the gasifier. The conditioning was operated for hundreds of hours and so on. The solid oxide fuel cell we never operate, okay. more or less for mainly for because we don't have a second extension. We asked for a second extension, and there is Jan Peter from Solidera that is very worried about his 300,000 euro. No, sorry, except for cell. It doesn't want to feed the syngas if not is really clean. Okay, so because okay, our also capability to analyze H2S, ACL, and so on is after. It's not online stream. Okay. And so, you know, and so we can say at the posteriori, after, okay, that maybe we respect the limits, okay. And in our test, we saw that we respect the limits in some condition. So, for example, this is becoming 4 or 5 hours in order to arrive to 800 Celsius degree, more or less, and we more than 2-3 in order to arrive to 300. Okay, and so we send the biomass and so on, and after we all combustion. After we shift to gasification, and so in 8 hours, okay, we are in a stable condition of operation. Okay, but in order after to have a stable operation for the hot gas conditioning, we see another 5-6 hours. Okay, so meaning after 12 hours. We reach condition that for us was good to feed the solid oxide fuel cell, but we have a prohibition of to send the gas. We have this for me is very pity because I'm more or less 20 years that I'm trying to feed the gasifier with molten carbonate fuel cell 20 years ago of Ansaldo and so on. After OME2, now with the Solidera solid oxide fuel cell. But I never arrived to feed directly. Okay, in lab many times. Okay, the bottom cell and the stack, but arrived to feed a system. Okay, but the good thing is that the price is decreasing here, mainly for the using of hydrogen for the solid oxide electrolysis. Okay, for the electrolysis, and so maybe the biomass sector also we will pyrolysis oil and so on also we will benefit from the electrolysis big plant production, okay? And so maybe we can use also, we will be able to use also the fuel cell at a low price for combined heat and power, okay?
Thank you, grazie. Any other questions? Yes, I'm coming.
Hi, Alan Sherrod here again. Perhaps I missed it in the beginning, but can you, why the choice of a fuel cell and why not a gas engine if the outcome was heat and power?
No, but this is very easy to understand, okay, no? I think that here, okay, this meaning, no, the solid oxide fuel cell, no, instead of an internal combustion engine can arrive to more than 50% also of electric efficiency. Our model said that we can arrive in our configuration at 49% of electric efficiency. Okay, so this means that first of all, you have better electric efficiency. Second thing, you have a stable operation, no emission. Okay, is no movement. A system not have movement. Okay, of course, this is good. You think that is good, but the problem is that is no a catalytic. So if you think about it, this is very too complicated system. Okay, you have two reactors, no, that cannot upset any kind of millibar of pressure. Otherwise, the syngas will go in the flue gas. The flue gas goes in the syngas. And there is a balance here of material. And here there is membrane, nanostructured membrane, okay, that cannot upset difference of millibar. And so, and these are not very, not the poisoning of that, no, is 1 ppm of H2S, okay, for example, no, and this means that we have a very low contaminants. So, why we try to use solid oxide fuel cell, I think is no, it's easy to understand because there will be higher efficiency, less contaminants, less emission, stable operation, okay, with no components in movement and so on. After, how you can use, how you can be able to feed this kind of system, not with natural gas or pure hydrogen, but with a syngas, this is another matter. And maybe with a double bed gasifier that you couple to a solid oxide fuel cell. But I think that at least we arrive to define the system and to build the system. This is the good things. And to understand what kind of price we need, okay, of the solid oxide fuel cell to be commercial, okay.
Thank you very much. We need to pass to Sol Free, please.
Yes.
You have 5 minutes left, so can make it
So,
10, but no more.
Sorry,
With
I
questions.
will go fast. Okay. So except for cell instead is not concluded. Okay, still is going. Okay. And instead is mainly in order a project when we try to operate different stack of different solid oxide fuel cell at different temperature, okay, with a common, okay, global system, okay, so integration of the stack, okay, and so we develop full operation window, no, operate that one from 0 to 100% of hydrogen and methane. Okay, so a common stack system interface for the different stack, no? And so a demonstration certification in order to operate this stack. Okay, so this mainly is that one. So for regarding the cogeneration, there is the possibility to cogenerate. There is already CHP that are fed by methane, no, and operate with solid oxide fuel cell. Okay, that have higher efficiency, no less emission. Okay, in some case when you can pay more for your CHP, no, you apply the solid oxide fuel cell instead the combined heat and power. Okay, of course. So we have made a stack characterization of these with different fuel. Okay, hydrogen, passenger fuel, nitrogen, and methane. We develop a stack system interface. Okay, that can be standard for exchanging the stack, no? Okay, and we develop also a system integration of this common stack. This meaning that I can operate with a common integration, no? And so if I have different stack that work at different temperature of the solid oxide, and if I have different fuel, I have hydrogen, pure hydrogen, I have pure methane, I have different percentage between hydrogen and methane, I can always operate the different solid oxide fuel cell. And this is in realization now, the system manufacturing by ICI Caldaie, okay? So we concluded the stack test, we developed the common stack interface, and we are building the system. And this system will be applied into different locations, exchanging the stack. Okay, more or less. Okay, this is being concluded. Okay, and so also here this is interesting in order to understand. Also, this will be because the stack is a cost, but also the system integration is a cost. And be able to realize a system integration that can operate different fuel can something that can allow to implement this heat and power. No, it's like alternative is like I say that more difficult is like with my gasifier I can put anything because I have a conditioning system that is always good and send the good things to the soft. Okay, here of course it's more easy because there is hydrogen and methane. It's more easy to do. Okay, but it's almost the same things. Okay, another project I would like also to show us instead is to always try to use this biomass, but for example go in negative emission, and so to apply also carbon capture. And of course all this kind of project we have to think about. I like only to say this slide because I always talk this slide for the ETIP, bioenergy. I also show in the strategic technology group, because this slide is tell to us that we have to work on the intermediate solid bioenergy carriers, okay, in order to develop legislation that is missing, and also a market for this kind of solid bioenergy carrier. And also we have to develop also a market for intermediate, for us, gaseous bioenergy carrier, okay. This meaning that these kind of things are integrated. CHP, biofuel, biorefinery, the biochemicals are integrated, okay. And so it's very hard, for example, to respect a target of 35 euro per megawatt hour of methanol biofuel production, of electricity 100 euro per megawatt hour, when you start from, for example, 30 euro per megawatt hour of a fuel. That is difficult to transfer and so on. And so we need, as the SmartCHP say, the project, is a common goal that we have together. For example, Blaise and GECO and also SmartCHP in order to develop this kind of a gap in legislation in order to go ahead with developing a market when this kind of solid bioenergy carrier and also gaseous and liquid can be the mainstream for the new chemistry, okay, and also can give a sustainable CHP production and biofuel production. Thank you.
Thank you so much, Enrico. We still have a few minutes for questions also for the last two projects. Yes, please. Introduce yourself, please.
Enrico, so I'm Michel Delaunay from Fit for Micro and Métis. So a question, so in SO3, as you said that you're comparing two stacks. So I saw Cogen.
Yes.
So which...
IKTS, from Fraunhofer Institute, okay, the other. Okay, I think it's written, maybe I go too much.
From
okay.
who you said?
Is okay. Fraunhofer.
Ah, the one from Fraunhofer.
Fraunhofer.
Okay.
Okay. No.
And do you see big differences actually in terms of behavior of the two stacks up to now?
Yes. Like? No, there is. Okay. No, the solid oxide fuel cell. No, sometimes still the production is quite not so much industrial. Okay, it's not like for example, they arrive to alkaline electrolyzer PEM. Okay, that you see almost industrial production. Okay, so still here we are in a few pieces a year. Okay, Fraunhofer is a little bit more advanced. Okay, and so he's already developed this facility in order to have 1,000 of pieces per year. Okay, that is mainly due to sell to the company. Okay, it's selling to company that want to develop this kind of technology, and so it's a little bit more standardized, and the performance are a little bit more steady. Okay, so I think that there is two differences. One is when you have some prototype that can still have to be. It's possible also to adjust something. Another, when you go in industrial production, that is more standard, the results, but you cannot change nothing, almost. Okay, so here I think that in the solid oxide fuel cell we are in this way. Okay, and so I think that for the electrolyzer, not for the market of the solid oxide fuel cell, they will go in standardized way in more than 10,000 pieces per year. Okay. And the problem that we think for the CHP market, that the current are 3 times more higher in electrolyzer mode and so on, okay? And so maybe will not give us the possibility after to change for applying the same stack for heat and power, for example, okay? So this is, for example, things that in this project we don't see too much. We see more difference regarding, of course, the 650 degree and 850 Celsius degree operation. Okay, 200 Celsius degree operation, but it's more a matter of application stability, reliability. Okay, because when you, for example, have a soft, you think that is always this kind of voltage that I have. No, it's always this kind of decrease from open circuit voltage. In reality, still is not in this way, okay? Because it's not still an industrial product, okay? So I see more this difference, okay? But I hope that will be solved because they will produce for electrolyzer. The problem is that, but we can take also for the CHP market. This will be. Thank you.
Thank you. Any other question? Okay. Thank you very much, Enrico. Grazie mille. Thank you. So we go to the last session presentation of this technology session, and that will be done by Michel Delaunay, who is a CEO at Métis here in Belgium, and is presenting us the Fit for Micro project. And it's very good, Enrico, you mentioned the joining forces between projects, and it's something the European Commission is promoting actually, so very good.
The more than I think 3, 4, 5 together meeting. This will be the 5, the 5th meeting that we're together.
I'm sure the European Commission is very proud of us. Thank you very much. Michel, s'il te plaît.
So thank you very much for inviting me for presenting So the new KIT project, because so I'm the new one here. So I'm delighted to present you Fit for Micro, which is an Horizon Europe project which started actually in October last year. So we are like roughly in 1 year. And the title is about the production of clean and efficient. So in this case, it's not only micro CHP, but CHCP. So we made it a little bit more complicated because we introduced cooling. And so to be complementary to the let's say the 2 other or 3 other presentations, so we are talking about micro turbines instead of ICE and SOFC. So I'm the CEO of Metis, which is located here in Belgium, and we are the coordinator of Fit for Micro and developer of the microturbine. So just to give you a little bit of overview of the partners and the projects. So we have 9 partners. This is a research innovation action. So we have a budget of the order of 5 million. We are 48 months. We started 1st of October, and you can see, faces that you know already. So BTG is there with Bert. And we have OE also, the Research Center on Combustion located in Aken and Fuels. University of Mons from Belgium, Fraunhofer Institute from Fribourg, Fahrenheit, which is working on cooling, Aalborg University from Denmark, and then ETA for dissemination, and Cogen Europe, which is helping us on cogeneration, understanding policies, markets, and so on. So the context actually behind the project was already recalled basically by the 2 other presenters. So we know that the European building sector is still using a lot of primary energy, still producing a lot of greenhouse gases. And if we look at, these are numbers actually that are dating from the proposal, maybe it's changed a little bit, but still, I mean, let's say 79% of all that energy goes to heating, cooling, and domestic hot water production. And at the end, I mean, that's a big number. I mean, 75% of it is still fossil fuel dependent. And of course, this is a big issue. And more or less, actually, another big issue is the fact that the building stock is renovating, but at a very, very low pace. So overall, actually, in 2050, even though we want to be carbon neutral, I mean, we still have a lot of buildings which are very old and for which you have to do something to basically heat them up correctly. So that's, let's say, started the idea of the project. And so we want to work, and what we want to produce here is a flexible renewable based, which will be also based on pyrolysis oil to some extent, a decentralized power, heat and cooling solution. So basically to meet our 2050 targets, which are extremely ambitious, so we know that of course we have to reduce our energy consumption, so we need to be better in many, many aspects. And we of course wants to replace the fossil fuels also that we are working in order to decarbonize, and that would require probably a mix of green electricity, but also biofuel from biomass and biogas to be produced. So solutions which are on the table today are mostly related to heat pumps, but that's with the also increase of the usage of electrical cars and so on. You can imagine that the amount of electricity which would have to pass by the pipes actually would be tremendous. So we would have a very high burden on electric grid if everyone would go on heat pumps, especially for old buildings. So we have also this idea of hybrid heating where you're mixing heat pumps and boilers. So many people are saying, look, I mean, okay, you have a nice heat pump, you have a nice boiler. At the end, it's only the boiler that is running. So, but also if you think about the heat pumps, it's going to be also a big burden on the electric grid, a little bit less than in the previous one. So the idea here is, the idea here is that we think let's localize power generation and heat production and cooling as well, locally into the building. That will decrease if you produce your own electricity with a certain type of fuel. You will decrease basically the requirement from the grid to let the other people actually who have a very good insulation building, they can use the heat pump. And so you want to have a very high efficient power and heat. This is also the idea of the SmartCHP project somehow, let's say, to some extent, that's also the idea of the other project which was actually proposed. So we are talking about decentralized power generation with renewable fuels, basically. And so in the project, what we are doing, I mean, we Metis actually are developing microturbines, so we don't develop ICE. We would like to go to SOFC, but that's going to be in a little future. But we are working on microturbines, and the idea is to build what we call a hybrid microturbines. Hybrid in the sense that it's going to be coupled with other type of systems, and mainly heat pumps. And this hybrid system, we'll use it for heating, cooling, and power, and then it will be working indeed on renewable energy. And at the end, actually, you want something that you can deploy that is producing high comfort levels to everyone, and also that is not too expensive. That's going to be in our KPIs, which I will not recall not to kill all the audience. And also with the penetration of the renewables at the household level, which is very limited for the moment. So the heart of the problem is this hybrid microturbine system. So you can see the cycle we are working on. So this is not a usual microturbine in the sense that a usual one would be basically a single stage machine comprising a compressor, a turbine, a shaft, a generator here to produce electricity, a combustor, and a recuperator. So this is typically a recuperated single stage microturbine, which you can find sold by different suppliers, which are my competitors, so I will not recall them. I'm just kidding. But in this one, actually, we want to go higher in efficiency than the usual 27% of a single recuperated microturbine. We want to go to 40%, which is a huge difficulty. And so to do this, we propose a two-stage microturbine. So you have an LP stage, a HP stage, high pressure, two combustors, so which means it's a reheat type cycle, and an intercooler. So at the end, we have what we call an intercooled, regenerative because we have a recuperator, reheat because we have two combustors cycle. And on paper, this cycle actually could reach more than 40% on paper. For us, in a small microturbine, and I haven't put you the power, so we're talking about something like 20 kilowatts, we believe that if we can reach beyond 33, 34% with this, it would be already very nice. That would be very nice. One thing that we do is we are combining this with humidification. So humidification means what you want to do is you want to recuperate some of the heat from the exhaust gas, produce steam with it, and reintroduce that steam inside of your cycle. And in fact, that's a way to actually balance a little bit in a different way power and heat. Sometimes you want more heat, so you're not going to do that. Sometimes you want more power, and then you can use humidification. So that's a way to balance. But you can push a little bit also your efficiency by 2-3 points. Hopefully a little bit more, but if you would get already 3 points, that would be great. So this humidification is already used actually in some big turbines. For small turbines, it's not used. And that would be quite of an interest actually to see how we can improve basically the efficiency of the system. Looking that for this system, basically what we want to achieve is indeed, as I said, like close to 40%. So what's important from these systems compared to ICE engine is that we are implementing flameless combustion. So that's a combustor that we are developing at Metis. So flameless is a technology of combustion which is a little strange because you think combustion, you think flame. In this case, you say flameless. I can explain you into more details later on, but what enables you is to get very low NOx. So you get very low NOx with no after treatment of the flue gas. So for example, for methane, we are able to reach lower than 1 ppm of NOx of production for natural gas combustion. Also very low soot, and also it's very applicable to many different types of fuel, so that's quite nice. Another aspect also that is interesting with microturbines that you don't find in ICE is the possibility to implement gas airfoil bearings, as you mentioned actually for your small blower. So we implement this also here, so it means we have no oil into the system. And for basically small systems like 20 kilowatt, 30 kilowatt, lower or even lower than that, it's hard to think that you can have oil into your system because that produces you a lot of problems in terms of maintenance. What you want is if we distribute these systems in a lot of buildings, you want the same maintenance basically time as a boiler. And a boiler is maximum, let's say, minimum 1 year of maintenance. So you don't want to maintain this more than with less than 1 year. So that's why we implement something which is no oil basically into the system. Very important, actually, we have the liquid biofuel aspect, which is coming from fast pyrolysis. So this is a continuation somehow of the SmartCHP project, but for microturbines. And I'll explain you a little later if I have time, but I think it's, yes, already. And then we combine this with a vapor heat pump. Same idea as what's presented by Bert, in the sense that if you have too much electricity, let's say, and you want more heat, just put it into a heat pump. You get more heat in that case, to do cooling as well. And also to use it as absorption for efficient chiller. Because one problem with the CHP is that when you're in the summer, you turn it off. If you turn it off, I mean, in fact, your return on investment becomes not so good. So what you would like is to be able to use the system all the time, and then coupling it, using the heat, basically, exhaust of this into an absorption chiller helps you actually improving your return on investment. Impact on this, I already mentioned, is basically the fact that we will, first of all, we want to really increase the technical performance, robustness, viability, and penetration of the renewables thanks to these liquid fuels. So in some ways, we are targeting also buildings which are not connected, for example, to the grid, and which cannot get basically in the future green biomethane. So they need to have something else, so they need to have liquid fuels. So we want to replace the domestic oil by basically the HPO, the hydrotreated pyrolysis oil. And you can see here an idea of where we want to sit basically in the different hydrogen to carbon ratio and percentage of hydrogens. We don't want something which is too expensive, but we don't want something which is too crude, because otherwise it's going to be very difficult to use into the machine. So we need to do something on the price. We need to do something also on the adoption of this kind of technology. And obviously, actually, hopefully by this project we can increase also our leadership to us, BTG and Fraunhofer. So I will skip. So we have in the project we have 8 work packages. So we have 4 technical ones, which go basically from the improvement of the biofuel production from the point of view of cost, but also from the point of view of nitrogen inside of the fuel, which is responsible also for NOx production through fuel burning. Combustion research, improvement basically of a flameless combustor for these kind of fuels. Then we work on the microgas turbine and the humidification. And then we go to the end, actually, into the hybrid system when we combine everything together. And then this is, of course, surrendered by the management, which we do, the dissemination communication. The LCA, we do an LCA analysis of the whole system and its impact in terms of gender and also general public, and also everything related to policy, because lots of things are actually moving today, and it's very difficult to keep up with all this legislation. So the project now is in 1 year, so we have results, some few results. It's very limited what I'm going to present because my time is very limited, but I just wanted to, Bert would do it much better than me. So this is basically the process of the production of the HPO. And we can have HPO with different qualities. And of course, the lower the quality, let's say, the lower the cost, which is better actually to distribute it to households. So we want to investigate which one we need actually for the implementation of this system. So can we do it with a relatively low HPO in terms of hydrogen content and therefore in terms of cost, or do we really have to go to the high HPO? If we would go to this side, which is indeed the classical fuels, the machine would work perfect, no problem, because machine works with anything, essentially. So in work package 3, so we and us, we are working on these combustors, and this is basically a sketch of our combustor where you see this, for example, here it's temperature, and you have no flame per se. So basically the combustion is taking place here, and it's very funny actually to hear this experimentally, because when you start the machine, you hear like this, which is the normal burner, but as soon as you move to flameless, you think that it's all extinguished, but it's still burning. Don't put your hand on it. So we are working a lot also on fuel atomization, because HPO for us is quite new. So we took our atomizer, we used it and we tested it, and here you see the diameters, the mean diameters of the particles and the statistics of it. And you see that, for example, here we get quite big particles, actually around 400 microns, and it's quite bad because that would produce soot. So we are improving this atomizer to a new one, and in the new one, for at least for domestic oil, actually it's very nice. So that's a work which is being carried out. And so this is an industrial, basically, atomizer, which cannot be used as it into our combustor for different reasons. So we are actually looking how to use it in order to reach this, but with our combustor. So that's our microgas turbine test rig. So we are testing it. So for the moment, but that's basically the core of it. This is the turbo generator, which is operating at 100,000 RPM, so 100,000 RPM on airfoil bearings. On one side, you have the turbine, you have turbine at 950 degrees C, and about 60 millimeter on the left, you have the compressor, which is operating at 120 degrees C. And all of this is without any oil, and basically your shaft is levitating in the air, which is very, very interesting. So Fraunhofer and some colleagues, they are working on where should we actually apply this machine. This was a big actually thinking into our project, which is basically, let's say, an important thing for selling it afterwards. What kind of building? So we've been looking at multi-family homes in different parts of Europe. Of course, it's easier to use it in Finland than to use it in Cyprus because of the heat. So where you have more heat, actually, it's better. So they developed a complete Excel system which is taking all the evolution of temperature during the time and so on. And we are using this to optimize at the end the system at, let's say, system level. But basically, a rule of thumb is a machine like this would like to run constantly. You don't want to stop it too much. That's a microturbine. So a microturbine is something that should be running all the time. And so our rule of thumb is basically that your heating power, maximum heating power, is about the power of your machine divided by 15%. So it means for a 200 kilowatt building, you can put a 20 kilowatt electric system with 40 kilowatt of heat. It's still okay. So that's good. So we are trying to narrow down basically where we can apply it as much as we can. Knowing that in fact these systems would be super nice if you combine them in district heating. District heating, and that would leverage a lot of issue because it doesn't care about which building actually you supply the heat to. So you put the machine into a building, it produces the electricity for the building, and then the heat, you dump it into the district heating and use it a little bit further. This is really great, in fact. So the Fraunhofer people are also working on our heat pump. So that's a Metis heat pump. It's a R290 propane heat pump test bench that we developed into a EIC accelerator project. So that's testing it to see what kind of performance we can get out of it. It's also very tunable, so they like it very much. And they're also working on an adsorption chiller from Fraunhofer with different types of adsorbent inside. LC analysis is performed by the Danish university, and in fact we had already a workshop on gender impact. For us engineers, I mean, it's very strange, but it was very, very interesting, in fact, at the end. And one important thing also in the project, another work package, is on the policy assessment, and there is new policies into the eco-design of buildings, which might not be so actually interesting for micro-CHP. So we want to see the impact of those legislation actually on the labeling, for example, of our machine. And the same thing with regard to the way actually you define bioenergy at the European level. What is renewable energy? Is our biofuel still considered as renewable energy in the future? So Cogen Europe is actually providing all of this to us as insight, and it's really interesting. So we've been doing a lot of dissemination still. So I'm happy to be here, but I've been also in Dubai, in different places, in Singapore and so on. So we've been quite active on this to send a message all over the world about what we are doing. And we have a bunch of new actually meetings which are coming, including EUBC in Marseille, but also Turbo Expo, which is for us very important in London next year. And I will tomorrow also be in Enlight in Paris actually to normally give a little word of fit for micro. Thanks a lot.
Merci, Michel. Thank you very much. So we are 10 minutes late, but still some minutes for questions before coffee break. Anybody? Quick question. Anyway, there's going to be time at coffee and
That's okay, no problem.
reception we're doing when we're finished. So I propose we start 10 minutes later, so at 3:50 instead of 3:40 for the people online. And then we will continue with our session on market and implementation. So bear with us because we'll focus on the market trends, so very interesting. And now let's enjoy a coffee all together. Thank you. about to start with the panel on market and implementation. So, as I said, we're going to focus on the market trends and the implementation of the solutions on the grounds. Yes, let me remember for the panelists that we have these technical issues, so please don't look at the light when you're sitting in the chairs, because if not, it can bother you. So this panel is going to be led by Atanas Bafea, Senior Consultant at Dowell. Let me remember that Greenovate Europe is a network of eco-innovation experts, and we're very proud of our work with our members. So Dowell Innovation is a member of Greenovate Europe. And I will let Atanas introduce the rest of the panelists, because I believe you have prepared a presentation.
Many thanks, Vicky. So, is it working? Yeah. So I am Atanas here, but I am not alone in the presentation. I would like to invite, we have Dimitris from Exergia and Kiel that who will contribute to the discussion today. Yes. Ah, yes. You have a. I can sit. I feel better. Okay. Is it good? So, Kiel, you are policy advisor at Svebio, and perhaps you can have a quick word about Svebio and your role in the bioenergy task force 4.
Yeah, I have worked with the Swedish Bioenergy Association for about 20 years as a policy advisor and communications director. I'm actually by training a journalist, and I have studied history at the university. So to me, much of the technical details here is not so easy for me to understand, all the fine parts of it. But I maybe think that I have a rather broad picture of how bioenergy works in Europe. I also have worked a bit with Bioenergy Europe. I have been chairman of our sustainability working group for a couple of years, and worked a lot with implementation and negotiations around the renewable energy directive in the last couple of years. And I also am a national team leader in Sweden for the task 44 of IEA bioenergy. And the subject of that task is flexible bioenergy and system.
Many thanks, Kiel. And we have also Dimitris Sarandaridis.
Hello, thank you, Atanas. I'm Dimitris Sarandaridis. I'm the head of climate change adaptation and resilience unit at Exergia consultancy in Greece. I hereby sort of represent the work that the team has done in SmartCHP. Personally, I have a background in mechanical engineering. I hold a PhD from Imperial College London on fuel cell technology. It was good to see some of the fuel cell work still coming to the front recent years. I will have a chance to say a few words more about the work we've done on market assessment for the SmartCHP project.
Yeah, many thanks. This is the aim was to have one of the difficulty of the exercise is we have seen different technologies, different conversions, different sizings, and to speak in general about cogeneration and bioenergy was a little bit tough. So this is why Kiel will introduce the session with a high-level discussion, and then with Dimitri, who will, as partner, Exergia is also a partner, as Dowell, who will show the work we have carried out within SmartCHP with a more focused view. So this just before we have seen a very interesting presentation, focusing more perhaps on the micro cogeneration. Here we'll see the mini cogeneration, but it was also introduced by Bert just before. Just one word on Dowell Innovation. So we are facilitator of innovation. So facilitator of research and innovation in different value chains, energy systems or smart cities or built environment, with different offer from the upstream, writing proposal, and here making some techno-economic analysis, but also communication and dissemination. Perhaps Exergia, you want to?
Yes, just a couple of words. Might not be familiar with Exergia. We're an independent consultancy firm founded in 1991, based in Greece. but we do have a really global reach, operating in more than 15 countries. We have 5 business units: energy markets, energy policy, clean energy transition, including RES, environment and water, and climate change adaptation and resilience. And we've been working with all the major donors and international funders, and diversifying really our budget and portfolio of activity across the globe. And we work across the spectrum of energy and environment, but we have some very strong experience in biofuel projects, and just a glimpse there of a few of the European Union projects we'll be working on. We can discuss later if you like. Thank you.
Okay, so now the floor is to Kiel. So if you want to introduce Vebio and what the task, it's...
Maybe I need to stand up a little bit, because otherwise I won't see the pictures so well. I can go over on this side maybe. Yes, Vebio is a regular bioenergy association. We were probably the first one in Europe to form a specific organization for bioenergy, the sector. And we have about 250 member companies. And in Sweden, bioenergy accounts for about 38% of the final energy use. So it's the highest share in Europe. And we also publish a couple of magazines, the Swedish magazine Bioenergy, and also the international magazine Bioenergy International, and its editor is here, Alan, and he's already asked a couple of questions. Let's see, we go on. This is how I see the trends for bio-based CHP in Europe. First of all, we have, of course, conversion of existing district heating systems and plants from fossil fuels to biomass and waste. And it's a rather dramatic development in some countries, and I'm going to show the picture of the development in Lithuania the last few years as the most interesting case, maybe. We see investments in new large CHP plants. The first bullet point there is about converting existing systems and existing plants, which I still think is the biggest part. But the second is that also new ones are being built, and often with a view of introducing BECCS, bioenergy-based carbon capture and storage, which then gives negative emissions. So this is an interesting path forward. But usually you need to have rather large plants to make it economically feasible. There is a growing interest, I would say, in middle and small scale bio-CHP, like we are discussing here today. And the reason for this, I think, is the high energy prices the last couple of years, both electricity prices and gas prices, and also the higher rate of in ETS, the emission trading system, and also the introduction eventually of ETS2, which is going to include then also small heat plants into emission trading, and also small industry. I'm going to give a couple of examples of what we do in Finland and Sweden. There is a growing interest in flexibility, and that's what we work on in T44. And the reason for this, of course, is that when variable power production from wind and solar increases as a share of the power systems, we see more and more problems with this, and there is a bigger and bigger demand for different kinds of flexibility in the systems. And finally, what you have also been talking about a bit before the coffee break is to use these installations not only for production of heat and electricity, but also for production of chemicals, or biochar, or biocoal, or pyrolysis oil, or whatever. And then try to find optimal solutions for this. Okay, so what do we mean with flexible bioenergy? This is a slide from T44, Task 44. The definition is that it is a bioenergy system that can provide multiple services and benefits to the energy system under varying operating conditions and or loads. And we give a number of examples there. It is, for example, technologies and concepts that can provide grid stability. It's a dispatchable production of energy and other products according to market demand. Also here we talk about cogeneration and long-term storage options such as biofuels and biochemicals. And of course this is the major advantage, as I see it, with bioenergy compared to other renewable energy sources, that our both our fuels and our products, intermediate products and final products, are storable. That we have the energy storage in the system itself. Which is very different from, for example, wind power, where you need to produce like hydrogen or something to, or a battery to store. This is, you don't need to look into detail on this one. We have seen many detailed slides already, but this is the only one of mine that is complicated. But it shows that, I think the interesting message of this slide is that bioenergy is not simple. The same way as wind power or solar. You have one type of conversion or installation for wind, three-winged wind tower or generator, wind generator, and it produces electricity. It's simple. But in the bioenergy case, you have multiple paths or solutions, multiple different biomasses, wet and dry and liquid, and then you produce a number of intermediate products. You can add hydrogen, or you can and so forth, and then at the end you have multiple applications at the end to use in transport or industry or heating or power production. So it's a complex system where you have to take advantage of the specific advantages of bioenergy, and try to find solutions that are economic, of course. That's the most important thing. They have to work on the market. One thing we do in T44 is that we publish on our website best practice examples. And I am in fact leader of that group in the task. And I must tell you, it is not so easy to find these simple examples of good flexibility that have been demonstrated on the market and that work well on the market. And I invite you from these projects we've heard about here before, the day that you have something up and running that is commercial and that can be shown on the market, then come to us and we will publish it on our website. But we see very little that is sort of advanced enough that is already up and running. But we see, of course, a lot of examples of more conventional technology where you can say that this shows that bioenergy offers flexibility services to the markets. We already have that, of course. I mean, CHP in itself is a good example of that. But here we have some examples. We have liquid winds production in Sweden, where they are now going to produce an e-fuel from carbon dioxide recovered from a regular CHP plant, and then they add renewable hydrogen and so forth, and they produce probably a fuel for maritime purposes. Several such projects, of course, are we see around Europe. This is biopower in Sweden. We produce every year a map, an updated map of all the installations of power production from biomass. And we today have 265 units with a total capacity of about 4 gigawatts. And half of the capacity actually is in the biggest cities in Sweden, in Stockholm and Gothenburg and Malmö. Much of it is based on waste, but most of it is forest residues or residues from the forest industry. And there are many of them are also turbines in the pulp mills. We have 95 biogas plants that produce electricity, and of course this is sort of the first step of small-scale biopower production that is also rather widespread all throughout Europe, particularly in Germany and in some other countries, but we have 95 of them. This is the Lithuanian example that I talked about before. I saw on some slide, maybe you come back to your slide, where you had some numbers from 2017, I think, which is, you know, quite a few years ago.
Well, that was when the work was kind of.
Yeah, that was at that time when you picked the numbers from Eurostat. But in that case, Lithuania still had quite a lot of gas, Russian Gazprom gas. And this slide only goes to 2020. And if we had taken another 2-3 years here until the current data, then there would be practically no natural gas left in the system. So you can see the total transition here between 2012 until let's say 2020. Where biomass and municipal waste took over the whole district heating system in Lithuania. Actually, they, as late as this summer, I think they inaugurated another big CHP in Vilnius for biomass. So they have done that totally, and they have had no problem finding sustainable biomass. This is a good example of one of these multi-purpose CHPs, which has been around for quite a few years. It's in Falun. I didn't write the name of it here. Falun, which is a city of about 40,000 people in central Sweden. They have added a pellet factory to the CHP, so they produce power, heat, and pellets. And the reason for this pellets factory, of course, is that they can extend the heat load through the year. So they run the pellets factory and the dryers during the low season for heat and hot water. And this is a chart of the system. And they actually also work together with another city, the city of Borlänge, which is about 20 kilometers to the side, and about a city of about the same size. And Borlänge has a waste to energy plant where they use municipal waste. So they take the base load from there, and then they run the CHP in Falun during the winter months. And let's see, let's go back again. And to produce electricity, of course. And also from the dryers they use heat for they use heat here for the dryers in the pellet plant. So they produce pellets for the community, they produce electricity, and they produce heat. And of course they have a hot water accumulator too as well, which almost every district heating system in Sweden has today, to be able to level out the demand and also be able to produce more electricity when the price is high, and then they can produce towards the accumulator, not only towards the district heating grid. So that's a good example of how you can adapt the district heating system to higher flexibility. This is an example of a city where you can see how you run the turbine in a system. This is the upper chart shows how they use the turbine and ramp it up and down. Oh, let's see, there. My fingers are too old. You can see down here. Here you see the electricity price through the year, or through this. It's actually a couple of years. No, it goes from 22 through 20. This is a period, 23 here, and you can see how it has been. It went up in at the September of 22. We had the big price hike in Europe because of the gas prices, and electricity prices went up as well. And this influenced also Sweden, so we also got much higher electricity prices than usually. And then you would think that they would produce much more electricity here in the turbines in Eskilstuna, but they actually didn't much. And what is the reason? The reason is that they have an obligation to produce heat, first of all, because that is what they're legally bound to do. So if they had a big heat demand at the same time, it's hard for them to produce enough. Or there could also be other reasons. I don't know exactly. But over here you see they got a much higher price, and then all of a sudden they produced much more. So, but this is of course a possibility also for a CHP to run to follow the demand on the market, based also mainly on prices. But it isn't, as this shows, just as simple as that you produce when it's a high price, but you also have to have the fuel, you have to have enough. Sorry, I think that my argument was wrong here. My argument would be that in this case, of course, they also need to produce heat. Otherwise, they wouldn't run the CHP. So, but later on, they also had a heat demand enough, and then they ran the CHP. Interest in small-scale bio-CHP. We had a conference a few days ago, Svebio in Karlstad, and we talked a bit about this. These are the arguments, of course, that I already talked about. The reason why we have this interest in small-scale CHP. 50 kilowatts up to 5 megawatts. That's the span I talk about. The high electricity and gas prices, the current prices, but also the expected higher prices. And then there is a wish, this is important, I think, the wish to be less dependent on the grid. We have heard a lot of people have contacted us and asked what kind of technologies are there on the market. One typical example is large-scale farmers who need electricity for in their animal husbandry for all kinds of equipment, and they are afraid that they are so dependent on the grid, both for the price, but also for delivery. So there is a fear of power outages. So they need a reliable power supply. And there are many other examples, of course, of industries and others who can use that. There is also a growing interest in using local energy sources, like harvesting residues and like landscaping wood or whatever. And this is also connected to the more difficult security situation we have also in Northern Europe, with a threat of disruptions because of political developments. And so we want to be self-reliant, and also people locally want to be that. We also have a problem with, at certain points to get enough effect in the grids into certain cities and so forth. Then, of course, we have the CO2 emissions. I talked about that before, that ETS2 can also be a driver here in the coming years. So the available options we have, of course, is either to use solid biomass, wood chips or pellets with conventional combustion. I mean, that is what you are up against, and with these new technologies, the simple way of doing it, the traditional way. Then we have gasification, we have pyrolysis, we have bio-oils. No one has talked about the conventional bio-oils. I mean, of course we can. We have millions of hectares where we could grow rapeseed in Europe, and particularly in Ukraine. And we have biogas, of course, as I talked about before. This is an example of a more simple technology, just to tease you a little bit, which is using just a regular combustion unit and a simple steam boiler, and you don't get more than 15% electricity maybe. But in this case, this company, VO, they are selling this simple system particularly to sawmills, because the sawmills, they need an awful lot of heat for dryers to dry the wood. So they don't care if they only get 15% electricity and they get 85% heat, because they need the heat. But they also need some electricity for their saws and their machinery and so forth. So this is maybe be a perfect solution for them. But it's and if you come and sell them something that is too complicated, you start telling them that we have to use such and such machine together with that machine and another machine and so forth, they are just going to say, forget it. I want something simple that I can rely on and that my guy here can take care of every day without it being too complicated. Yeah, I only have one slide left. This is another one. This is a little Finnish gasifier. It's only 50 kilowatts electricity, but it's also working with actually a gas motor. They are running this motor with gas that they produce in this little unit. We have all been a little bit wary of this one because they didn't do so well a few years ago on the market. They didn't work so well, but they sold a lot of them in Japan. So maybe they have improved it, so it's working today rather well. That was my last picture.
Okay, thank.
It's Walter. Yeah.
Thank you, Kiel. Many thanks for the wide panorama, including a country like Lithuania, sawmill, and the Swedish situation. So we have 12 minutes to finish from what I said. So I will ask Dimitri to be quite quick. So now we will plunge into SmartCHP with the market assessment.
I will need this.
Yeah, thank you. So
thanks, now I'll skip that.
And
Don't
I will
worry.
conclude directly on the second part.
Thanks very much. Just to begin with, big disclaimer. Thank you, Kier. This work was done before the war, so it's likely things might have changed since in terms of data. This is our market assessment approach. I'll talk a bit about the first two pillars, essentially trying to understand what's the market out there, what's happening in terms of CHP, and then narrowing down, try to identify our customer base for the technology we've been developing in the program. Capacity-wise, there's large variation from country to country in Europe in terms of CHP. Germany is by far the leader, followed by Poland, Netherlands, and the Czech Republic. Now that's across scale. If we were to focus on the medium scale, we're talking about up to 1 megawatt electricity. Germany is still the leader, but we also have Belgium, Italy, Netherlands, Denmark, and the UK leading. On the right-hand side, we see the percentage of contribution to the electricity mix of CHP. Now that generally fluctuates between 11 and 12% on average in Europe, but again, large variation from country to country, leading Denmark, Latvia, Netherlands, and Finland. And we saw that we know also the fuel choice varies a lot in CHP systems, and not traditionally, natural gas was the fuel of choice, but green sustainable fuels and less biomass has been increasing in the mix. In this snapshot, we have leaders like Sweden, Finland, and Denmark. So a promising landscape for use. I'll skip this one because we're going to talk about driving factors later on. So what we tried to do was to focus on a select number of countries to do more in-depth analysis of identifying the market base for our system. And we started with over 15 indicators across various activities, like policy, regulatory context, energy markets, and feedstock sources for every country. And we came up with a list of these 10 on the left, covering a whole bunch of range of regionality and fuels. And then we needed to narrow down even further to 5 to do our case studies. So we came up with that list, essentially trying to still cover as much wider region as possible in Europe, and also a range of feedstock choices and options. And then which were the sectors that we were to potentially see our smart CHP system materialize. So for the scale we were talking about, we identified mainly tertiary service sectors and one agricultural sector to focus on, hotels, office buildings, retail, we're talking mainly about shopping malls here, hospitals, educational buildings, and greenhouses. And through an iterative process of a large number of assumptions, we came up with a number of potential units that could use the smart CHP technology. Essentially, we assumed 50% use coming from cogeneration and 5 to 10% out of that could potentially come from the smart CHP technology. So essentially, we could really, even very conservatively, estimate that over 100 units or systems could be a potential market for these select countries moving forward. Independent of the maturity of the technology, if we were to look at the macro environment factors that really will affect the implementation and the realization of the technology. Mainly, of course, we've got biomass availability, which is critical, policy and regulation, uncertainty, and how this we can incentivize or not the use of the technology. But also, equally importantly, energy prices uncertainty and how we've seen how these have fluctuated in the last few years. And Thanas will touch upon that a bit later on. You can find the full report. It's available online for all the details. I'm happy to discuss also later. Thank you.
Very efficient.
That was good.
Many thanks. So because it will let some time for the discussion. So thanks, Dimitri. So let's continue the discussion. So the main conclusion, as you have seen, is that we have the 5 countries and the usual suspects that are on the right, which are the tertiary sector for this class of use between 100K and 1,001 megawatt electric equivalent. So these are the overview about the six market segments in terms of million of square meter that are per type of segments. So this was the conclusion of the D6 one. So now if we go to the techno-economic analysis, in order to assess or to make some prevision and some projection regarding the profitability or the gap to profitability, we need to go on a case by case. So this is why we need to make specific studies for each of the segments. So there was one activity on the use case selection. So this was introduced by Dimitri. And then I will spend 1 or 2 minutes on what are the most impacting factors for profitability for this kind of technology. A few words on CapEx and OpEx, and then on the public monography. So we have seen the different, the market study paved the way and introduced the techno-economic analysis on these countries and the 6 market segments. So we implemented 4 use cases in Greece. So thank you, Exergia, for all the data I provided, because on the bottom line, it's all the difficulty of this kind of analysis is how to find the data, which type of methodology, the granularity, the interpretation of the methodology of the results, and debug the things, and then the communication and the visualization. So these are the 4 classical things upon which we need to pay some attention. Most impacting factors. So the first one, which depends on the local energy constitution, is the feed-in tariff. How can we valorize the reinjection of electricity into the power system, into the grid? The second factor is the energy price. Of course, this was introduced. It impacts a lot according to the price. And the intuition from Michel, this just before, was very correct in terms of what makes the things profitable in terms of use in the winter time of cogeneration. Then OPEX and CAPEX. So here comes the operation mode of the unit, of the engine, and then the CAPEX, of course, impacts. Again, the disclaimer is that at the end of the project, we are at TRL5, and from TRL5 to TRL9, the projection on CAPEX might decrease. This is experience curve, it's industrialization stage, and this is a little bit conservative. The CAPEX at TRL9 will be lower than a TRL5. So I will take just the illustration, some illustration of some factors. So regarding the cost of gas and electricity, this was introduced by Kiel. You can see multiplication by 2 and 3 between the start of the project in 2019, so the statistic of 2018, and 2022. So you can see country per country, the effect on gas and electricity with multiplicative factors that are important. And of course, at higher price, the competitivity is easier to reach. Now, on CAPEX and OPEX, what can be said? We had in SmartCHP some contractual KPI, Bert, you know that very well, of 1,000 kilo euro per kilowatt here. So we'll try to yes, this one. This is for the target KPI. We'll see the results. And for the OPEX, we are around 10 cents the kilowatt hour, 100 here for the electricity and 5 cents for heating. So what are the results? In terms of CAPEX, we are quite online, at least for there is a threshold around 250 kilowatt electric. That is a kind of turning point here. Above, we are on good shape, so the KPI are met. On the small system, it's more tricky to make the profitability on the CAPEX and target here. So you can see the results at this point at an average mini cogeneration based on the assumptions we made and by the partner ABM. This was the results that were shown. On the OPEX, the situation is hybrid, but we can see that on the electricity, which is on the bottom, the KPI is there, so we are quite comfortable. We have a margin. For the heat, it was a little bit above, so the results were not so favorable. If you combine, of course, it's not very scientific to combine electricity and heat, but we can say that globally, the heat and electricity KPI in terms of operation scenario are met. And I fully agree, Michel, with what you said. Here, it's not written, but we have 3 operation scenario. One was 8,000 hours of operation, of flat operation during the year. So this is OS1. The second one was a day and night, but it's not very convenient to start and stop at every day, but it's a theoretical archetype of operation. And the third one, OS3, is perhaps the one that you criticize, that is a functioning like a heating machine on winter time. So, and again, we need to find the other way of valorization, because just an energy machine and heating machine is not sufficient to make the things happen. Visualization of results. So these results will be available on Zenodo, so I don't have time to detail, but you will find 7 monography of the same type, including the description of the case here. So here is an hotel in Greece. The type of use in terms of energy, sorry, I am also energy needs, sorry, so okay, I cannot reach it. Here the energy, the design of the machine, some of the results in terms of breakdown, a monthly breakdown, and some sensitivity analysis in the end in order to make the things according to the price of electricity. So soon available on Zenodo, the public deliverable. I don't know how much time we have for the discussion. It's short. Yeah, we are almost ahead of time. So I will skip this one. I want just to insist, it's a kind of conclusion regarding the drivers and barriers. There were a lot of nice intuitions that were discussed by the previous presentation, even though when we are in the micro cogeneration with the small, the SOFC, the fuel cell, the solid oxide fuel cell, or the turbine, which are smaller size. Here we are on the mini cogeneration, so it could be above 100K in terms of electricity, but there are some commonalities. So I've tried to list that in terms of multiple value that we can capture. So of course, the first one is energy value. If the system is not sound on the technological standpoint, and the efficiency is poor, it's difficult to cover the profitability by the other type of values that are the flexibility and the non-economic value. But from your presentation, you mentioned energetic autonomy, sovereign energetic autonomy, the CO2 emissions, the short circuits, the local values, the green values. So there are a lot of things that are probably missing. There is one which is missing. It's all this is about energy. There are also, you mentioned chemistry, I think, or high added value molecular that could be extracted from biomass, and perhaps it might be other source beyond the stricto sensu energy that could play a role. So I don't know if we have time for a debate, but I think it was quite living. We need to move to the next one. If there are questions, I will be happy to answer. Yeah, Bert.
Maybe one question.
Yes.
Maybe one question for all three of you. You mentioned here the barriers. What is the most important one according to your expertise? Maybe for all three.
The evident answer will be TRL5 at the end. So Kiel mentioned something very interesting, that people want mature technology. Yeah. If you want to be convincing, but Kiel, go ahead.
I still think the cost is the biggest barrier, because basically economy is what people drive companies at least, but also utilities and cities who want to have heat for their people. They want to have the lowest cost, because it's their taxpayers and the customers don't want to pay too much. So I think when we talk about drivers there, the incentives like emission trading or feed-in tariffs, or that's important. Really, we're going to discuss that more, I think.
If we have time, yes, Dimitri, you want to?
I'll just add another dimension which probably was not mentioned today at all. It's more social and has to do with trends and fashion and things that can be appealing at a certain point in time. So timing sometimes is essential, and how a technology might be promoted or perceived by select people, a group of people that may be controlling, what might be fashionable as such. I'll just give an example of fuel cells, for example. They've becoming on and off for the last, 50 years, and they're doing cycles. Hydrogen, now it's become really hot. It was hot also 30 years ago, then it became stable. So maybe trying to find a way of making, say, for the lack of a better word, if we try to make it this maybe a bit sexier, sort of in terms of a solution that can appeal to the social imagination in a way that they can see that part of their daily life. I'm just adding another dimension, which it's not the most important probably, but does play a role, because we live in an era of image.
Yeah, there is a cultural dimension.
Yes,
sure.
Exactly. So, thank you.
Any comments or questions, or from the grid? No, you don't. No, from a chat. So thanks a lot. Thanks again for the speakers, and see you soon.
Thank you, Atanas. Well done. Thank you to the three of you. So now we will go to the last session, policy session. And we will be obviously focusing on policy and regulation to bring and to foster the solutions and the use of the small-scale CHP in Europe. And I will give the floor to Thomas Slecker. I'm hoping to pronounce right your name. And you will be presenting, as you come from the General Directorate on Research and Innovation, and you will be talking on research and innovation policies for bioenergy. So thank you very much for being with us today, and the floor is yours.
Thank you very much for the kind introduction and also for the invitation to this very interesting event. Indeed. So, yeah, I will talk a little bit about, I think I stand over there, European R&I policy on bioenergy. I think also, as we heard a lot already on policies affecting flexibility, etc., as an additional prime, I think, to the discussion we will have now. Of course, the European policy framework is very much embedded now with the European Green Deal, where you see here already there are really the main objectives to become climate neutral by 2050, but disconnected with environmental sustainability. I mean, there's a big focus on protecting human life, animals and plants, by cutting pollution. This also links to biodiversity in our context. Then competitiveness of European companies, very important, and also the social inclusiveness, and this is also very important for energy. Of course, this builds upon a big package of EU sustainability policies, one on the climate and energy side, but also a set of environmental policies, relevant legislation there, Natura, for example, but also for basically all the areas of the biosphere, and also sustainable investment policies. I think to mention here is one example, of course, the taxonomy and sustainable finance. Now, deal. I think you're all familiar with the Fit for 55 package. Then we have the red revision. What I do not have a slide on, but I think it's important also in what was already presented is, of course, the energy system integration strategy. I think is very important for the sector to look at, with a strong focus on electrification, but also with measures for other sectors. Sorry. And so a lot of individual measures here. And recently, of course, with Repower EU, an additional momentum for getting independent of Russian oil and gas, and with big boosts in that range of sector. What I mentioned here is, I think, the boost for biomethane in this context. And now looking at competitiveness, also the Green Deal Industrial Plan, which looks also of the competitiveness of individual technologies really needed for this transition. I go quickly through that, but I think you will share the slides later on. And I think also one example, we talk a lot about the electricity market, feed-in tariffs were presented. The necessary revision and the Commission proposal for the revision of the EU electricity market design, which brings in indeed this flexibility theme, but also rules for enforcing, or let's say from the consumer side here, and also new support schemes for demand response and storage. Now, and I think we touched in the previous presentations on the high energy prices in the last years, and I think you also looked at these energy prices. This came up by your presentation in particular, and also this wish for independence. I think energy poverty is also one important issue we need to think about when we think about sustainability of the solutions provided, and this feeds back, I think, to both CAPEX and OPEX in this context. Now, very important also for bioenergy is, of course, biodiversity and the sustainability criteria. I mean, without going in detail, but of course, bioenergy is under, let's say, clear observation there, and we see now the strengthened sustainability criteria applicable, and I think this is also what your projects look at with the feedstock diversifications by going more to residues and wastes as a possibility. Also, of course, always considering this need to optimize both the sustainability as well as the cost of the biomass you feed into your system. What we do here, what we do in the Commission, there is also the JRC biomass mandate, where Commission Services gave a mandate to JRC to look overarching at biomass supply and demand, now nearly 10 years ago. And this work, for example, also feed it into the forest biomass sustainability discussion. You might have seen the relevant report. Now, going to what is the R&I policy in this respect. So, of course, now we are dealing with Horizon Europe, and I'm pleased also at this event we look at the transition of Horizon 20 to Horizon Europe, because, of course, we are looking at the continuous development of the portfolio over many years. The general vision of Horizon Europe is also to really contribute to UN sustainability goals. And I think this is really important for bioenergy. And on two sides. First, you have, as you all know from the projects, you have clear requirements always regarding sustainability in the topics. But the development there is, I think, which you see in particular in Horizon Europe, that it's not only environmental sustainability, but we try to look at all three dimensions of sustainability. And then also, if you look at UN Sustainable Development Goals, you can find interrelationship at least, but often a main impact on many of these SDGs for bioenergy is possible in this respect. And I think this is an additional maybe driver for the development, if it is done correct. It's on one side, of course, let's say a boundary which you should not cross to not be unsustainable, but it can be also an additional push to advocating for these technologies. Now I present you more what we do in Pillar 2 in the work program Climate, Energy and Mobility. And here on one side we have the Clean Energy Technology Observatory, where we actually task JRC to look at all these technologies. And you might also, this includes bioenergy, also the biofuel and renewable fuel technologies. And this is yearly, the reports are yearly co-published together with the competitiveness progress report. So if you might find it via the Energy Union Competitiveness Progress Report, and all these reports feed in. We will have more independent reports on also on system aspects where we look more and overall sustainability. They will are forthcoming. So here indeed we look also at the interface between systems, technologies, and also horizontal, for example, sustainability. So this is a little bit analog to what you do in your project, where you also look at the technology and you look at the system and then the related factors. So we are also looking, let's say, on the portfolio side at the same indicators or criteria. Here's, for example, what we think about. We have this aim to really, with this observatory or JRC colleagues, we gave them the mandate, but have really to aim to expand from environmental sustainability also to the other dimensions. So this will be ongoing work, because there are also, of course, several challenges about how to put this all together into an overall framework. Now, what is the European R&I strategy on bioenergy and biofuels? I think the main lines we address, the main sectorial challenges, which are cost competitiveness, and I think this came also very much out of your presentations. Then, of course, high environmental sustainability of bioenergy value chains is a must for novel technologies. Also to expand the feedstock basis and how we can system integrate it. And here, of course, flexibility is one of the examples to address specific sectorial needs, mainly for the biofuels is another example, like for aviation or maritime. Now, what we have, I mean, this is only a selected section of the bioenergy topics. We have here, of course, we heard already about, this is now only about Horizon Europe. I didn't bring up the Horizon 2020 topics yet. We heard one ongoing project, of course, for the first on cost-effective micro-CHP and hybrid heating systems. We had a topic open on demonstration of large-scale CHP technologies, where there was no submission in that area. Then ongoing the evaluation of the topic on development of near-zero emission biomass heat or CHP, including carbon capture, and development of forthcoming development of carbon fixation technologies for biogenic flue gases. So we are not only looking at the core of CHP technologies, but we have also innovative renewable energy carrier production for heating from renewable energies. So we have also topics, let's say, more downstream or upstream of the value chain, which are interesting for you. And please look also out of the box in other areas of Horizon Europe if you find something which can be of interest for you. With this, thank you very much for your attention.
Thank you very much, Thomas. I think we can take a few questions. If any, yes, please, Bert.
If you go one slide back, do you have an example of the last one? What is meant there? Or
now I didn't bring the topic text together, but I think it is the integration of other renewable energies also. So it's not only strictly on biomass focus alone, but feeding in other elements. But we have to look at the topic text. I didn't bring it. I do not want to now. I do not recall all the details. But please look at the topic.
Yeah,
and so, but in general, we have quite some. We have classical topics, really on the bioenergy area. But we have also topics really combining now, in spirit of energy system integration.
I think we have one more question.
We have been rather disappointed that both in Repower EU and also in the Net Zero Industry Act that modern bioenergy solutions have not been even mentioned from the European Commission. This is very disturbing to us because Europe is leading internationally in these kind of technologies. Why did you make that kind of a choice?
Well, I'm not representing the lead DG in the discussion. I'm from DG Research Innovation, but I think there was a prioritization of some of the technologies which are in particular important. I mean, this doesn't mean that there are not other set of technologies also addressed. But I take your comment as such. Thank you.
Thank you. Please stay with us because I believe you're a member of the last panel that we are about to start. Thank you very much. And which will be led by Martin Vies from BTG, Senior Consultant. And I will let you introduce the rest of the panelists as I believe you prepared. Yes. And this is the last session. Yes.
Yeah.
We can take another turn.
Yeah.
Yeah, because of the light.
Oh, okay.
But you better stay this side, otherwise you're going to be in the screen. Okay, right.
Yeah, the light is a little bit better.
Thank you. And then you have this for the slide.
Okay, great. Thank you. Yes, very welcome, all three of you. Dominika Lange from Cogen, Policy Officer. Irene Di Padua, also a Policy Director. And you're also involved a lot in policies, so I'm happy that we can talk that in much detail. We have a project at TRL 5, and yeah, we found, we identified already some barriers, very specific ones. I will present them very briefly. And then I would like to ask you, what can we do about it? And what would be your way to present solutions to the Commission? I think that is also part of your job. So I'm really interested in that. We have seen the policy framework just presented very well already by Thomas. I found here 2 targets important, the rest 3. It has a target for renewable heating and cooling, which is about a 0.8 increase per year in the first years and a 1.1 increase. The RED 2 had also this type of numbers, but now it says shall, so it shall be done, so that's good. Energy efficiency directive, we see energy efficiency targets, and I found also interesting member states making comprehensive assessments of how are they going to use to make energy efficiency happening, also including CHP and renewable heating and cooling. And the main, also very interesting, local heating and cooling plants. It is something new for each city, more than 45,000 inhabitants. They will have to make a plan, and they have to include high efficient CHP and renewable energy and heating and cooling. So maybe, we can be there part of that. Well, the role of smart CHP, if I look at the share of renewables in electricity, it's going very well. It's really going well in Europe. The heating and cooling is lagging a little bit behind and should be increased a bit more. So here's an opportunity already. And of course, as said, this type of solutions have a limited impact on the electricity network. And if I look at my own home country, the electricity net is full, and still a lot of wind parks have to be connected, and we have lack of people who can put the cables there. So maybe we were going the next year to a point in timing that we can have a smart CHP system as a good solution. I hope so. Another thing, and here I will have the specific issues that I encountered. Of course, the whole system is very unknown still to policymakers, so it's really great that we are here today to tell about it, so the general public will know it, policymakers will know it, and I think we should somehow make that it's also this type of smart scale CHP included in those national energy plans, comprehensive assessments, and especially in the local heating and cooling plants. For the rest, we found out that emission limits for installations of less than 1 megawatt, there's no EU legislation, so each member state has its own legislation. I think I'm actually happy with the medium combustion plant directive that has emission limits for 1 megawatt and more. And many EU countries use that emission limit, so that's good. Maybe we should ask for emission limits for smaller installations as well. The problem is of the eco-design directive is only for small-scale installations that have been proven and have been in large quantities here, which is not the case for smart CHP and these small-scale systems. And then again, I think the main barrier, I would say, is if we have to have a full environmental permit, this will be a real barrier to implementation. The medium combustion plant directive is okay. Member states can ask only for a notification, but they can also ask for a full permit. So I hope they really go for the notification. But then, of course, new technology, we have to give them comfort, these people. So I think we have to work on a SEN standard for this FBPO in combustion in engines and have a testing and measurement program. And then, of course, the end of waste status needed for clean biomass. I believe the Waste Framework Directive could maybe be changed in a way that really clean biomass can just be used for products. It's also good for circular economy purposes. So this is a whole list, but we had also a whole list of all technical stuff, so I think we can also have some policy stuff here. Dominika, do you think, is this list a little bit complete, or do you think you forget a lot of barriers and it's worse than this?
Well, I mean, yeah, for sure. I mean, good afternoon, everyone. Once again, yeah, I'm representing Cogen Europe. Just to mention briefly, it's the European Association for the Promotion of Cogeneration sector. So we are a cross-sectoral voice for the cogeneration industry. So yeah, we are our day-to-day work it's mainly focused on cogeneration, including micro, CHP, and small-scale cogeneration. We were also involved in a lot of EU-funded projects. Also, we are a partner of the Fit for Micro project, which was presented today. So yeah, we had some experience when it comes to the policy and micro and small-scale CHP, and I would say that there are several perhaps things which are missing, but have already mentioned them briefly. So to say it briefly, because I think that we are running already out of time, I would say the main policy barrier, which I would say for me it's a top one priority, it's the fact that actually there is no single European Union regulation or directive actually that governs the use or uptake of micro CHP technologies. So actually jurisdiction to develop those policy is primarily devolved to member states. So we have different policies towards micro small CHP, which makes it difficult for the mass commercializations of this technology. And also if it comes to EU and its policies, I would also say that on the other hand, micro CHP has been mentioned, as you said, it's mentioned in the EED or the EPPD regulation, so the regulation concerning buildings. But actually you have some of them which are really which really fails when it comes to really giving the true energy efficiency and decarbonization potential of the technology. And here I mean the eco-design and energy labeling, where the methodology they're used, it's really affecting the energetic class of the technology itself. And it results in the fact that this technology, it's not well recognized across EU files. I mean, EU different policy files included in the Green Deal and Fit for 55. And also maybe two additional things which are also perhaps not mentioning, but the fact is that when it comes to the policy, the energy, heat and gas systems are quite, even though the Commission has its energy system integration strategy, all the different energy carriers are quite separated when it comes to different policy files and targets. So actually, the EU really missing on hybrid solution opportunities, which could be achieved also with the help of micro CHPs. So yeah, I would say that's the main things just come to the top of my mind on the spot.
Yeah, thank you, indeed. A single directive for CHP, micro CHP would be ideal indeed. Yeah, I think that's a good idea.
Would help.
Yeah. And Irene, you are also a policy officer for bioenergy Europe. What do you think are real, important barriers for small-scale biomass CHP systems?
Yeah, so, well, first of all, good afternoon again, everybody.
Yes, of course, yeah, please introduce yourself.
Irene Policy Director at bioenergy Europe. We are, I guess most of the people in the room knows what bioenergy Europe is, but maybe for those online, we are the European Bioenergy Association. So we do cover pretty much the full value chain for biomass uses for energy, which goes from very small scale to CSP, to power, to heat. It really depends on the needs and situation. And I think the good thing of speaking at last, because we had quite some interesting conversation already during this afternoon, is that I can just complement what, I mean, most of what I think has been already said, and I think your list is also quite comprehensive. It's true that we do have a gap between MCP directive, the medium combustion plan, and the eco design, and that we also have some concerns of the energy labeling, because that's also under revision, especially for smaller scale. There is no connection between energy labeling and eco design. And there is also a suggestion on the table, a proposal to merge the label for local space heaters and boilers with heat pumps, which they are quite different systems with different purposes, and we believe this will be counterproductive in the overall increase of efficiency and lowering of emissions of these systems. But something that I see missing here, but this came out a bit in the conversation, and I think we'll touch upon that later as well, is the misconception around bioenergy and the awareness about these solutions. Because, as Dominika mentioned, there is not a legislation which is directly let's say, dealing with micro-CSP in particular, because Renewable Energy Directive, the limits are much higher for sustainability criteria. This is above 7.5 megawatt thermal, so we're talking about much smaller scale than that. And eco-design as well, we do have a gap. So there is a bit of a, let's say, legislative vacuum when we talk about these subjects, which I don't think makes really the policies the main barrier, but it's several factors, including indeed awareness, concerns about the use of bioenergy, and also the capability at local level to get to these solutions. Because sometimes, if you think about local authorities, they don't have they cannot afford the cost of this transition. So that's also something which I think brings more complexity to this conversation in a way.
Yeah, thank you. Yeah, thank you. I can also, yeah, indeed, more complexity indeed. Yeah, Thomas, thank you for your presentation. I've heard something that I found very interesting. That you said indeed GRC has this Clean Energy Technology Observatory of new technologies. So, what could what could SmartCHP project after this project ends do actually to make to promote our technology? Should we go to the GRC and talk about it, or maybe you have other suggestions how we can continue, of course, going to a higher TRL, going to this valley of death, and then hopefully commercialize this technology?
So what the GRC colleagues do is actually for all the technologies in our portfolio. So to analyze them on a yearly basis now and to update always the technology status of innovative technologies, as well as to assess the market view on those technologies. And colleagues are, of course, looking at the projects, but I invite you to look at the reports which were published, and there are also you find the respective authors, so you could inform them also on your results. I mean, to spread the results of your projects. And I think you have also interesting policy briefs of the projects, which, I mean, coming to this, what you said about the regulatory challenges, I think from, of course, we are not in DG RTD, not the lead DG for regulatory issues, but for us it becomes interesting when innovative or new innovation meet, of course, new challenges and what can be the solutions there. I mean, generally we address this a little bit in our market uptake topics, where we look a little bit what is the landscape for new technologies to enter the market. But I think indeed, coming back to observatory, this is an interesting exercise. It actually continues work we had before also with the JRC, which was the Low Carbon Energy Observatory. So it's actually a continuation now over several years to get in-house expertise in the assessment of a whole portfolio of technologies. It doesn't look precisely as individual projects, but how the overall field will develop.
Yes, thank you. Yeah, we will,
One question, is it a public assessment? Is it available, or is it an internal? Sorry. Is it a public assessment, and is it available, or is it just for internal use by the EU?
No, the reports are public. You find it in cities, but a good link to find it is via, so the last reports you will always find co-published with the competitiveness progress report of the Energy Union, which is a yearly report on the competitiveness, and there you will find the link to the current reports, at least those on technology and market.
Thank you. I think the moment is there. We have a panel. Are there any questions from the public to this panel? I heard, for instance, Enrico, he talked about legislation gaps, so maybe you can say a little bit more about that if you would like to. I'm curious.
Yes, no, I think that, no, they discuss about the active that I think is very good. Okay, in some delegates, the active delegates of the RED 2, for example, okay, there is some indication about the type of biomass that you can use, no, the sustainability and so on, but there is no too much indicator about all the type of waste. Okay, so we need a detailed classification. Okay, because this kind of think about no, we say that mainly the biomass is no agri-industrial, no, for the field is forestry. Okay, no, from the forest. Okay, and after this all the kind of waste, multi-gaseous waste and so on. Okay, we cannot use directly the biomass, no? We use the waste biomass, the secondary biomass. Okay, this secondary is a plethora of secondary. So, for example, no, if I can use no, the woods directly, I am a normative, I can calculate and so on. Okay, if I use a secondary waste, sometimes I don't have the normative and so on. Okay, and so there is missing gap in order that I can say that I can use that one and can say in this emission and so on. Okay, these things is missing. Okay, if you want to, for example, apply for pyrolysis, for gasification, and some specific secondary waste, okay, you are not covered by specific, or you are at a standard and use pellets, use chips and chip of wood, this kind of wood, and this is standard. But if you use strange, but it's not strange, different secondary biomass waste, no, you don't have specification about that. Okay, and this is a problem in order to apply this in the market. But first of all, for us to make a calculation in our European SS project. Okay, but second, okay, thank you.
Yeah, thank you for your contribution. Yeah. Oh, yeah.
No, thank you very much for the comment. And indeed, I mean, we always want to know, of course, what are the new challenges, let's say, for innovative projects. And I mean, you mentioned one of the examples. Thank you.
Okay, thank you. Yeah, I think. Or just a final word, maybe, because we are. I think we have to round up. But maybe you have some final words for us.
One short comment on other feedstock, indeed, rather than woody biomass. I mean, right now there is also discussion about including agricultural biomass in eco-design, for instance, which will also, let's say, expand a bit on this issue of having different streams of feedstock. But it was just a minor thing. If you want, I can go ahead with my final remarks, since I think we are running a bit out of time. I would just like to make a consideration on the fact that I think we are looking at a shift in the energy system as such, because until a few years ago, well, first of all, it was much based on fossil, which unfortunately is still the case, even though we are working to get rid of them, and was also much centralized. While right now I think we are having more and more decentralized solutions, more renewable solutions, and I think there is really a change in how our energy is produced, which really will put the focus on the local aspect as well. And in this context, I think it's quite key to highlight which are the local benefits, because when we talk about biomass-paid CSP, the feedstock most of the time comes from the local level. So we really have an added value in the community. And if we look at energy imports, so what is actually used in Europe is 96% of the feedstock comes from Europe. Just 4% comes from Canada, US, some trusted streams. So I would say this is also something to stress in promoting these kind of solutions, because it's really cheap, renewable, and locally available. Just this.
Thank you.
Yeah, and just maybe add to that, I would say, if I can maybe something which I could really encourage you for to. It's perhaps since we all know the benefits when it comes to small and micro CHP and the cogeneration itself. I would say that it will be essential and actually crucial for as many stakeholders as possible to be involved in those forums and platforms and meetings which are actually run and organized by the EU institutions, European Commissions, in particular DG Energy, because that's the place when you can really raise your also like the benefits of the technology and also your concerns when it comes to the market or where you can really discuss regulatory and administrative barriers. And we need this policy support to be able to introduce those technologies on a much wider scale than it is today. And also we need this financial support, which is currently, in some countries, it's even less than it was 1 year or 2 years ago. So this really helps in creating this favorable, I would say, policy environment for our work. So I would really encourage you to take a look on those issues which are going on at the EU level and be vocal. Thank you.
Thank you. Thank you. Thank all of you for your recommendations today and your presence here. And really great to have.
Thank you,
this
Martin.
Yeah.
I think we can close a big applause for our panelists. So we have come to an end. Yes, James is making me the sign of drinking. Before that, before we drink, I wanted to thank James and Piero from Greenavate Europe team, of course, all the consortium, but James has been very silent today, but he's been the project manager within Greenavate Europe with the great support of Piero and all the team. So also Simon, thank you very much. Well, I'm not going to go again through everything we've seen, but it's been great to see from the technological, the market, and the political point of view all the work ahead, but also all the possibilities and challenges that we have discussed. It is, as we said at the intro, the solutions proposed have a lot of, they're very sustainable from the emissions point of view, but also from the financial point of view. But there are a lot of challenges, still some barriers, as we have discussed. It's great to collaborate with other projects. So thank you very much for Enrico and I don't know, no, the other gentleman left. But thank you very much. Thank you to everybody. And yes, we have a wine, a reception waiting for you outside to mingle, to discuss, and to continue discussing all the possibilities. So thank you very much. Thank you, Bert, for a great coordination. And always welcome in Greenavate Europe. Thank you. And almost on time.